Hey.
Hi. 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 Hello. I'm IXS. I'll be your Herald Angel for today. And we have a service announcement. On Friday, that is tomorrow, the talk Relaunch Bits of Freedom, which is supposed to be here, will take place in the Two Envelopes tent at 1600. And the Tempest for the Casual Election Hacker is at the Monty Hall. So please keep that in mind if you're interested in these two talks. Thanks. And now it will be a real pleasure for me to announce Leslie Devan from MIT. She's here to talk about a cyclotron to generate particle beams, if I'm not mistaken.
Yep.
Thanks. So please give me a hand of applause for Leslie.
Hello, my name's Leslie, as said before, and just to introduce myself briefly, I'm right now a grad student in nuclear engineering. Is the audio having problems? Oh yeah, that's a lot of audio. Louder! Louder? Wait, like this? Okay, I'm sorry. All right, so this cyclotron work is based on research I did as an undergrad for an undergrad thesis project in nuclear engineering in spring of 2007. And, well, so this will be telling you how to design and build a 2 MeV cyclotron, thereabouts. So to start at the very beginning, well, no. So the way this is being organized, we're going to start with development and applications of cyclotrons and just generally what they are. Then going for about 10 minutes or so into the necessary physics governing equations. And then we'll be spending the rest of the time on component design, so talking about the vacuum chamber, electrodes, the RF system, impedance matching, and particle generation and detecting the particles. So now, just starting very basically, talking about what a cyclotron is. So it accelerates charged particles. Those are things like electrons, protons, or heavier ions using an electric field. So it has 2 electrodes, accelerates the charged particles across that field. And they have to be charged particles because you're accelerating them using an electric field. So if they were neutral, that field wouldn't do anything to them. And furthermore, there's a magnetic field in place, completely separate from the electric field, that confines them to a spiral flight path. And this is important because the spiral flight path means that it's more efficient than a linear accelerator. So I guess I don't have a board, but so imagine you have a linear accelerator, some protons at this end, voltage applied here. The protons are accelerated across this gap just once. So you need a very, very high voltage gap or a long distance or both to get very highly accelerated particles. But in the cyclotron, like you saw on the previous slide, it's a spiral path, so it encounters the same accelerating electric field many times. So these typically generate energies on the order of 1 to 5 to maybe 10 mega electron volts. Generally around 1 to 5. The entire system is inside a vacuum chamber. We're going to be talking more later about why the vacuum chambers are especially important. And just brief line of historical background, first developed in the 1930s. There's a picture on the right there of the first cyclotron developed by Livermore. just for particle physics experiments. Now they're used for medium intensity radiation sources and starting stages for larger accelerators. So something like this, the type of cyclotron that I'm talking about today, would be useful for a high school level, undergrad, college level physics lab type thing. Now, just an introduction to this before we start going into the physics equations. This is the vacuum chamber of the cyclotron that I built, and they're the numbered ports on the side coming off. There's the RF system, which has the impedance matching, port 1, then a vacuum pump to maintain the low pressure. Ports 3 and 4 relate to the ion source. You have the electrodes for that, and then also a hydrogen stream that's for generating the protons. There'll be more on that later. And then 5 up there is a target to collect the accelerated particles. So the physics, and this part, it's simple physics, but I'm not sure what level physics people are familiar with. So if I say QV cross B is the force, how many people are down with that? Just show of hands. Okay, cool, that's reasonable. So if people are more interested in learning the sort of electricity and magnetism you need to understand this, it's fairly simple level stuff, even for the cyclotron. But one of the best books is Purcell's Electricity and Magnetism. It is classic. It's dear to my heart. It should be dear to your hearts as well. So just a bit more on the QV cross B here. So these are, if you have a charged particle that's moving at a non-zero velocity inside a magnetic field, there's a force that acts on this. And that force is given by Q, which is the charge in coulombs, times the velocity. That quantity, which is a vector, crossed with B, which is the magnetic field. And the cross product there, bear with me for a bit, this will be useful and good. So the cross product there, it's not just a simple multiplication, but it takes into account the vectors and the directionality. So basically, there's something called the right-hand rule, which is useful for evaluating cross products. It tells you what direction force the resultant acts in. So take your right hand. Sweet, yes, interaction. Take your right hand. Thumb is the direction of the velocity of the particle, so you have a particle moving like this. Let's say you have a magnetic field that's directed in the direction of the rest of your fingers, then the force acts where your palm is, like that. So V cross B is the force, and then Q is just a scalar. So, so this applies to our cyclotron because the cyclotron vacuum chamber, the sort of pie plate circle that I showed you before, has a powerful electromagnet that applies a fixed field in a direction across it. So you have your particle starting out with a small velocity in one direction, like that. Your magnetic field, the line's pointing down, for example, starts moving this way with a velocity. Force pushes it this way, so now your velocity vector goes like this. So you curves, keeps curving, force is pushing, and it starts moving in a circle. And there's a picture of that if you enjoy pictures. So basically, yeah, so you have a plane that's demarked by V and B, and no matter what, the force is perpendicular to the plane that those two vectors make. Right-hand rule shows you the direction in which you're being perpendicular. Now, talking more about the spiral flight path. So you have the force is QVB right there, and, well, just the scalar quantity of the force. And that's a centripetal acceleration. And just the formula for centripetal acceleration is mv squared over r. That's just a set thing for a thing that's being curved. So then you take the second two parts of that equation, rearrange them, you get the velocity is qbr over the mass. So now you have an equation for the velocity of the particle in terms of the charge, the magnetic field, whatever its given radius is, and the mass. And those are all known. Now, so there's that same velocity, which we derived in the last two slides. And this, this shows how you go from the circular flight path into a spiral flight path. If you look at that first bulleted equation up there, you see that the velocity is in the numerator on the left side, radius is in the numerator on the right side. Q, B, and M are all fixed quantities. Those aren't changing at all. So you increase the velocity, the radius is going to increase. And you're increasing the velocity every time the particle goes across the gap between the two D-shaped pieces there. Because when it goes across that gap, it encounters the electric field. It's accelerated, velocity increases, radius increases, so it spirals out until it reaches the end of the cyclotron, where you have a target. Now, there's again the velocity equation on the top, and there's a thing called the cyclotron frequency, which is, well, how many times per second it goes around the circumference of the cyclotron. So that's the velocity divided by 2 pi r. 2 pi r is the circumference. So velocity divided by circumference gives you per second the units. And so you solve for that, subbing in the velocity equation up there. You get qb over 2 pi m. And the interesting thing about this, the most important part, is that it's independent of radius. And that's really why cyclotrons work. Because it means, well, going back to this slide. So it's not a constant electric field. The magnetic field is constant. The electric field oscillates. You can see the square waves oscillating coming up there. So you have to oscillate the electric field at a certain frequency to accelerate the particles at the right time. Wish I had a pointer. That would make that a bit more clear. I'm sorry. So basically, you have to switch the electric field back and forth. Does anyone have a long stick by any chance? Well, no, I'll just gesture. So basically, when the particles are on, this isn't working, on the lower side of the cyclotron, you want, oh, thank goodness, whoever's shown a laser in that direction. Thank you very much. Thank you. Okay, so you have, did I break this? Excellent. Okay, so you have your particles that are starting out here, cycling around because of the magnetic field. They end up at this point. So let's say these are electrons. So you want to apply a positive voltage here, a negative voltage here to accelerate your electrons across that gap. Then they curve around like this. They end up here. So now you want a positive voltage on this one and a negative voltage on this one to accelerate it there. So you see how you have to switch the polarity of the two pieces at every revolution. And so because the frequency is independent of radius, like when they get out here, the particles are moving a lot faster than they are in here. But it's timed correctly so that for all of the particles, you can switch it at that same frequency, given by that equation. So, and yes, as I said, the signal that you apply to the two electrodes, it has to oscillate at that frequency f. Now, okay, kinetic energy. So this is what I was talking about earlier with the 1 to 5 MeV. I'm not sure if this is review for anyone, but so kinetic energy of a particle is 1/2 mv squared. You know what v is because that was what I put on the top of the last 5 slides or so. Substitute that in, you get q squared, b squared, r squared over 2m. So just for example, for the cyclotron I built, these are not in the ideal units, Tesla, coulombs. You end up getting an energy result in joules, and then you can convert that to MeV. So 1.96 MeV, around 1, 2, 3 MeV is standard for this size type of cyclotrons, type of magnets you'd be able to build, etc. Now, in general, the most important factor that affects the kinetic energy that you'll be able to get out of the cyclotron is the strength of the magnetic field. So if you have a larger magnetic field, there's a greater centripetal force pulling the particles around. That means you have a tighter spiral, so each particle encounters the accelerating electric field more often. So you end up getting particles with a greater kinetic energy. Just a brief review of, brief thing showing the different reactions you can drive at different energies. This would be applicable for well, never mind. So reactions you could drive at the energies you have. Oh, let me talk about this notation quickly. So this is nuclear reaction notation. So looking at the first one, you have lithium-7 that's going into beryllium-7, and the P comma N in the middle means you're slamming a proton into the lithium-7, and you get out a neutron and beryllium-7. And so for the next one, again, you have beryllium-9, put in a proton, you get out a deuteron and beryllium-8. And just showing that graphically, my 9 boron is having some problems, but yeah, so that's the third reaction there. You have your 9 beryllium with the 5 neutrons, the 4 protons. You put in an additional proton that knocks out, so you put in the additional proton, you see now that there are 5 protons there in the 9 boron, and it ejects a neutron, only 4 neutrons there, 5 neutrons there, and now you have boron 9. So that's the type of reaction you'd be able to drive with these. Transmuting light elements into other light elements. Okay, so that was all the necessary physics, so it's not very much physics. So now we're going to go more into the mechanical, some electrical engineering side of things. Now, the vacuum chamber is the most important part, and in my opinion, one of the hardest pieces to build because it involves a lot of fairly low vacuum design. You have to use also magnetically transparent materials such as aluminum, copper, brass, things like that, because steel, even a lot of stainless steel, has some ferromagnetic properties, and so that would cause eddy currents when you apply the magnet to it, and that would disrupt the field. It would become very uneven. You couldn't accelerate particles through it. Also, the chamber has to withstand very large forces without significantly deflecting. And that's because you have the very low pressure on the inside, atmospheric pressure on the outside. If the walls aren't thick enough, it just collapses like a soda can. And this is a bit annoying because you have to do this design with aluminum, whereas steel, like steel of even a small thickness, would be able to withstand this force easily, but doing it in aluminum is slightly trickier. So for vacuum chamber design, there are 2 main things you have to think about, and those are flight distance and mean free path. So the flight distance is the length of the spiral under ideal conditions, and that, as we said before, depends on the magnetic field and the voltage applied across the electrodes. So the voltage applied across the electrodes and the distance between the electrodes gives you the electric field, which is accelerating them. Now, on flight distance, there's a MATLAB simulation that I'm going to post to the wiki, I guess, and then link to another website. I'll give you details on that at the last slide. By a MATLAB simulation for a magnetic field of 2.7 torr, 1,000 volts, applied to the electrodes, you get a flight distance of about 300 meters. This is in a cyclotron chamber, which is about 8 centimeters in radius. So you'll have something on the order of that. So now you know what flight distance is, and easy MATLAB or OpenOffice spreadsheet simulations will tell you what those are. You have to take into account the mean free path. Now, the mean free path is the length of the spiral under real conditions, and that depends almost exclusively on the vacuum pressure. And so that's because, as you can see on this slide, if you have a very, very low vacuum, almost a perfect vacuum, you only have a few air molecules inside your chamber. If you have a less than ideal vacuum, you, of course, have more air molecules. The problem is you have your electrons, your protons, your heavy ions that you're accelerating. If they encounter any one of these air molecules in your cyclotron chamber, they'll lose energy and go off course. And the combination of those two means that they won't hit your target if they hit a single air molecule. So you want to keep the vacuum as low as possible. Now, well, here it's just kind of cartoony illustration of what mean free path is. So here are free paths. Here, the distance it travels before it hits something, take the average of those, that's the mean free path. Now, there's a pretty straightforward equation for mean free path where, well, kT over P sigma, with T is temperature in Kelvin, K is Boltzmann's constant in terms of joules per Kelvin, P is the pressure in pascals, and sigma is the target's cross-sectional area in square meters. And that's basically, you have your atom. It kind of looks like this. What is the 2D projection of cross-section? Now, an interesting, I think I have time for my interesting aside. So I'm a nuclear engineer in general, and cross-sections are used fairly commonly in nuclear engineering. And the unit for cross-section in nuclear engineering is, well, it's one that makes a lot more sense than square meters. It's something called the barn, which is 10 to the minus 24 square centimeters. And the reason the unit was called that was, I think back in the 40s, scientists, well, US scientists, the Manhattan Project, were looking at the cross-section of uranium-235 and uranium-238. And the cross-section for uranium-238 was like, 10 orders of magnitude larger than they expected it to be after they did their experiments. And they were like, wow, that's as big as a barn. So that's why the unit is called that, 10 to the minus 24, because it's really, really big compared to other things that are smaller. Okay, so there's the mean free path equation again. So to minimize particle loss, you want your mean free path to be significantly greater than the flight distance, like an order of magnitude, 2 orders of magnitude would be ideal if you can get it. Though it's tricky to get it because it's expensive to get vacuum pumps that are good enough. So you want your vacuum pressure then to be around 1 or 0.1 pascals, which in atmosphere is 10 to the minus 5, 10 to the minus 6. So that's pretty low. You definitely can't build a vacuum pump like this. But one of the wonderful things is that these show up on eBay fairly regularly. Like I just checked a few nights ago, and there are 3 that are suitable for this that cost under 150, 200 US. So these can be bought. And they have to be bought, really. But that's the sort of thing you need to get the vacuum pressure low enough so your particles don't strike into air molecules. Now, a bit more on the mechanical side of things. So as I said before, you have to use magnetically transparent materials, aluminum, copper, brass, things like that. It's useful to run some simulations to determine what the deflection is, because it's basically a circular plate that's fixed at the edges with a large pressure gradient distributed across the surface. So if you have access to SolidWorks or finite element software like ANSYS Adena, it's useful to run a sim like that. That'll also tell you how many bolt holes you need. I did a bolt pattern of, I guess, 16 for that radius. Just make sure you don't have any large stress concentrations in the material. It works well to do an aluminum body and then brass bolt holes through it. Just from experience, aluminum screws don't work or exist at these pressures. Now, safety factor is another thing to consider rather. I feel like such a mechanical engineer talking about this here, but yeah, safety factor. It's defined as the maximum stress that the material can withstand divided by the maximum stress that the material will likely encounter during its service lifetime. And in general, safety factors for things are like 2 or a 3. I was kind of a pansy, so my cyclotron had a safety factor of 4, but it's really your choice. You want the safety factor in place because, for example, what if you run your vacuum at a lot higher than it's supposed to? This will buy you some leeway so that your chamber doesn't crumple. Now, 2 types of aluminum that are good to be aware of. I'm not sure how much people know about these types of aluminum, but 6061 is the cheapest type of aluminum. It's standard, it's very easy to machine. I use this for the body of the cyclotron because that can have thicker walls, so it's not under as significant stress. Top and bottom lids, it's better to use aircraft grade aluminum, 7075. That's really, really annoying to machine, but you can make it smaller, so you'll be able to fit the cyclotron inside a tighter gap, which is useful depending on the type of magnet you're able to buy or make. Now, just talking about those two parameters, Young's modulus and yield strength. Young's modulus is effectively the springiness of the material. It's like a spring constant. And the yield strength is the stress at which the material first starts to deform plastically. So it deforms and it doesn't spring back into its original shape. So those are useful when you're considering safety factor. Now, one of the most important things about vacuum chamber design is to make sure that it's actually a vacuum. And for that, you need to put in O-rings at the top and the bottom. So the vacuum chamber, it has three pieces. I guess I didn't say this explicitly before. You have the ring-shaped piece here, and then a bottom lid, and then a top lid that's not shown in this picture. Pattern of bolt holes, O-ring groove on either side of the body plate. And also Teflon tape here to seal the port feed-throughs to the body. These aren't welded, though it's possible if you have access to a TIG welder, you could weld those pieces on. Now, in a bit more detail about the port feed-throughs, so you want to use tapped holes, ideally with an NPT threading. That's just one threading specification that's especially good for low-pressure applications. And just wrap Teflon tape about it. On the website, I go into more detail about this. And then that holds up to 10 to the minus 3 torr, very low. And you want to use rubber O-rings, Viton or Buna N, for the gland design. There's also a very good website on gland design. I give that URL there. And that just shows things like, well, if I have an O-ring of this diameter with this cross-section, I want to make the width of the gland this much, the depth this much. So it's straightforward. Also, a brief aside on the type of O-rings you should use. Rubber O-rings, yes. Teflon O-rings, you don't want to use those. Those are for like rotating applications, so. Okay, so that was the end of the vacuum chamber design section. Now, going into the RF system, here's just an overview of that there. Here, top view of the cyclotron body with one of the electrodes and then feeding into the RF box. There'll be a more detailed picture of that in a few slides. So the way, do I have another picture of that? Okay. So the way this works, you saw in some of the earlier slides that there were two D-shaped electrodes where one of them would be at a negative voltage while the other would be at a positive voltage, and then they'd flip-flop at the cyclotron frequency. So mine I did slightly differently. So you have one copper D-shaped electrode here, and then the body of the cyclotron, and this would go between a high voltage and a negative voltage, and then the body of the cyclotron, which is connected to this copper plate there, would always be held at system ground. So basically, you have one D-shaped D, and then the other D is the entire rest of the cyclotron system. Now these, the electrodes, this is what I'm calling the electrode right here. You can make them out of copper, which gives you better conduction, fewer eddy currents, or brass, which is easier to machine. If you have access to a water jet, it's easy to water jet out two half-circular shapes and then just braze them onto a strip there, so you have the hollow D-shaped piece. And then just water jet out the rectangular piece as well. Right, so as I said before, the square wave is applied to the D-shaped piece, while the rest of the system is constantly held at ground. Now, impedance matching, all right. So while we were talking about mechanical things, the RF feed-through, which I showed you before, that was the aluminum tube that led out to the box. You need to prevent that piece from arcing because you're applying fairly high voltages to the inside of that piece, the copper rod on the middle, while the aluminum tube on the outside is constantly held at ground. So you want to fill it with something like Delrin, which is a type of plastic, to prevent it from arcing. So you can do that pretty easily just by getting the aluminum piping, press-fitting Delrin inside, and then press-fitting your copper tube, and that'll give you a vacuum-type feed-through, which won't arc. Now, impedance matching is important. The vacuum chamber and electrode system, it acts as a capacitor, which makes sense. So you have something at one voltage, something short distance away from it at another voltage. So it's a capacitor, albeit a big, funny-shaped, spread-out capacitor. Now, you want to, good, that's working. You put the system in parallel with an inductor, and just from basic current analysis, it resonates at a particular frequency, which is given by 1 over 2 pi root LC, where L is your inductor, C is your capacitor. So they're in parallel on the circuit diagram. So for example, well, this is your function generator, this is a variable capacitor that we're getting into later, this is your inductor, this is your system capacitor, and that's ground. Now, you have your signal coming out of your function generator that's at a fixed impedance. It's at 50 ohms because that is what they come at. And you need to match your system to this 50 ohms, or else you'll get reflection and you'll lose a lot of your power. So the way you do this is by adding in the variable capacitor, which allows you to adjust the total system impedance. And the resonant frequency remains unchanged by adding in that capacitor. So an easy way to do this, it's difficult to get inductors that are at the inductance that you need, but it's straightforward to make them. So you take some copper wire. This is just 8-gauge copper wire, I believe. Wrap it around something. I used a broom handle. And once you get a coil of maybe 10, 12, 15 turns, you use a network analyzer to measure the resonant frequency of 2 particular systems. So you take your weird hacked-together pseudo-inductor coil, put that in parallel with a capacitor of a known value, figure out what the resonant frequency is. At that point, since you know the value of the capacitor, now you know the value of your entire inductor. Then you take your entire inductor, put that in parallel with the vacuum copper D-shaped system, check the resonant frequency. That tells you what the capacitance of your vacuum system is. So you have that number, which you'll need later on. Now, what you have to do, you need to, assuming your magnet is at a fixed field strength, you'll need to tune your inductor so it matches your cyclotron frequency that you calculated before from those variables. So you need to tap off of the inductor at a given point to measure that. So basically, you hook your capacitor and that inductor up to your network analyzer, and then, well, with your brazing torch, because that's what you need to attach to something as thick as this reliably, you tap off of the inductor at different points along the coil, so different numbers of turns of the inductor are in your system. Keep moving it and moving it and moving it until your system is at the frequency it needs to be at. Oh, and then you use your variable capacitor to adjust the impedance so it's at 50 ohms, and then you're done. Well, you're almost done, except you need to test for arcing. So a good way to do this is basically you set your function generator to put in pulses of, say, 100 watts at a given frequency, and then you tune up your oscilloscope and you make sure that it's giving you a constant output. If the output varies over time, that means you have arcing going on. If it's constant, that means everything is peachy. It's useful also just to look at the quality factor. I'm sure everyone here knows what a quality factor is. So basically it's the, well, you have your bandwidth, you have your peak frequency, it's one divided by the other, everything is great. So, okay, back to the mechanical side of things. You need to shield your RF system to keep it from, well, from stray pulses that might be coming in. So just housing it in something like an aluminum sheet box is enough for that. You need to ensure a consistent ground. So if you braze on copper flashing to connect your inductor coil to your system capacitor to your ground, that'll be good. Delrin standoffs to prevent arcing. So here are just the BNC connectors to your function generator here and up here. So if you just make little standoffs out of Delrin, keep the system from arcing. Those, just as an aside, are the gauges of wire I used, but that obviously you can change depending on what you want it to be. Also, well, this is a bit of review from before. So you need a function generator and an amplifier. This is what you're applying to the copper Ds. These, I guess it's technically possible to build your own, but probably it's easier to already have your own or buy them from eBay. So ideally, you want to apply square pulses at the system's characteristic frequency, or sine waves also are, those are fine too. That's it for the RF system. Now, last two things we're going to be talking about. Oh, good, and there's time. Talking about the ion source and the ion detector. So for my system, I was accelerating protons. I think in a few slides I'll be talking about problems associated with accelerating electrons. So for a proton ion source, you're using electrons to ionize a stream of hydrogen gas. And ionized hydrogen gas is protons. That's where they come from. You generate the electrons using something called thermionic emission. Now, good, a slide about that. So what thermionic emission is, you have a conductor that's at a high temperature, something like 1,000 to 3,000 Kelvin. Hot conductor. They have enough kinetic energy. They have all this temperature, so they're oscillating very fast. They're moving, they have mass, so they have kinetic energy. Enough of that to escape from the bonds that are holding them to the surface of the conductor. So these electrons overcome the electrostatic binding energy, they jump up. Now, if you have a source that is more positively biased than that conductor, the electrons then are accelerated towards that positive thing, because that is what electrons do. So in this system, an easy way to do this is you use a neodymium filament. A neodymium filament gets very, very hot if you apply a fairly small voltage about it. Okay. That is negatively biased. So you apply your 10 volts, 15 volts to that. The electrons have enough kinetic energy, start jumping up, and they start going to, because it's negatively biased, ground is positive for them, so they start jumping up towards your system ground. So you have a constant stream of electrons flowing from the hot filament to the system ground. And just to go back to this slide, this is the coiled up neodymium filament there. And then the electrodes for that, and the hydrogen stream. Now, right, and this just shows you need about 10 volts to get the 1,000 Kelvin for the thermionic emission, because it has just 22 ohms of resistance, that coil of wire. Right. Now, the second thing you need is the hydrogen source. Now, this, you can just get regular tank of hydrogen fairly easily, but the tricky thing is you need a needle valve. You can buy these used, they're kind of expensive to get them new to the tank outlet. And needle valves are important because they're very good at maintaining a very constant, very small flow of a gas that's coming out. And these, good, I have a slide just for those because they're important. So, constant calibrated, low flow rate over very long periods of time. Very long periods of time meaning a day or something. Now, they have a small opening there with a long tapered seat. You have a needle-shaped plunger, which is on the edge of a fine threaded screw that fits in that seat. So you turn your valve here, that goes out just a bit, and then you're able to get a small stream coming out, well, in the direction of out of the screen. There. That's the inlet this is the outlet there. Can't just use a regular valve. Now, right, as promised, here's the bit about electrons. So when you accelerate charged particles on a curved flight path, you get something called Bremsstrahlung radiation, which is basically photons in the soft X-ray range that come out perpendicular to the flight path. Now, if you're accelerating protons with the sort of magnetic fields that you can readily get, the protons don't get fast enough to have Bremsstrahlung radiation, but if you accelerate electrons, they do. So you have X-rays pouring off of your detector, which are bad for you and other people standing near. So you need to put lead bricks around it if you decide to accelerate electrons. Now, it'd also be a good idea, so if you're accelerating protons in the way that I mentioned before, you'll probably also have some stray electrons from the thermionic emission that are coming out, so you want lead bricks anyway, but it'd be far, far more of a problem if you're accelerating electrons. And for the detector, this is the last bit, which is good because we're kind of running out of time. One of the simplest ways of, if you just want to detect your protons or electrons or other ions and not run a reaction, is to use something called a Faraday cup. Now, schematically on the right, there's a Faraday cup. You have M+, which is just indicative of any sort of ion there. Thank you so much for this laser pointer, by the way. Striking the metal detector here, so you have an ion hitting a metal detector, the charge goes up. Not by a very large amount, because it's just an ion, but still, it increases. And you just have a meter that is measuring the electric current as it goes to ground. And so in practice, what you want to do is to connect the metal to a sort of capacitor to increase the signal to noise. So it fills up the capacitor and then discharges. Or if you want a very fine-tuned value, you can just hook up your ammeter directly to the piece of metal that has the ions impinging upon it. Now, here's a photo of one. This is not from mine. This is from the Rutgers Cyclotron. I'm going to post the website for the Rutgers Cyclotron. It's very detailed, very useful information on there. So you have a copper rod in there, which is connected to an amplifier. That amplifier is connected to, well, through the ammeter to ground. You also need an electron shield on the back side of it. So you have your protons, which are oscillating like this, they're positive, and then you have oscillating in the opposite direction, or rather spiraling in the opposite direction, you have your electrons. They're going in two different directions because they have different signs of their charge. So you need a shield on the back of your Faraday cup, because otherwise your electrons impinging on it would mess up your count. They would nullify a large number of your protons. Now, the nice thing about these Faraday cups is that it's fairly easy to incorporate a linear actuator so that you can slide it in and out to check your count at different points along the flight path. So if you want it all the way at the edge of your vacuum chamber, you get a fairly large count. If you want it all the way in, or sorry, you get the higher energy, or you can move it in, and that's useful for troubleshooting. And just to review what we were talking about the last few systems, port to the RF, a port number 2, which would connect to a vacuum pump for maintaining the lower pressure. Ports 3 and 4 are for your ion source. Port 5 is the Faraday cup, which you can't quite make out here. Now, those sum up basically vacuum chamber, ports that connect to the vacuum chamber. The last important piece that we haven't really talked about yet is the